Hi, Professor.
Hello.
Hi.
Hi.
So we are going to go back, okay?
Yeah.
So just a minute. Okay. So hi everyone. So welcome back for this afternoon section. So for this second lecture, we have again Professor Anthony Leggett with us to present his second lecture on exotic firm superfluids and superconductors. So Professor Leggett, if you want, you can start. Okay, we are
Okay.
all here. Thank you.
Well, in this lecture, I'm going to talk about some of the what are often called the exotic superconductors. The reason they're called exotic is that until about 1975, we thought that we really had a pretty complete theory of superconductivity. It was actually based on the ideas of my former colleagues, John Bardeen, Bob Schrieffer, and Cooper at the University of Illinois. Crudely speaking, it was a theory in which you started from a free electron gas and then put in a weak attraction due to the exchange of phonons, lattice vibrations. And using that model, Bardeen, Cooper, and Schrieffer, BCS as we usually say, we're able to calculate a large number of properties of the superconductors known at that time. And for about 20 years following their discovery, that seemed to be the complete picture. Nothing was discovered which seemed to be inconsistent with that picture. But since 1975, things have changed quite a lot.
Hi, Professor. Are you listening? You you
Okay.
were
Sorry,
muted.
did you hear that
Uh,
part?
we lost some of the things you
Okay,
were
why don't
saying.
I start again?
Okay, yes, thank you.
Um, as you probably know, there is a famous theory of superconductivity, which is due to my former colleagues, Bardeen, Cooper, and Schrieffer, usually abbreviated BCS, at the University of Illinois in 1957. In that theory, you start from a model of free electrons and then put in by hand a weak attraction between them. And that attraction is believed to be the result of the exchange of phonons, lattice vibrations. And using that model, one can calculate all sorts of thermal and transport and whatever properties of the system. And for about 20 years after the original work of Bardeen, Cooper, and Schrieffer, most people thought that was the whole picture. But since 1975, we have actually discovered a whole gamut of new superconductors, which in one way or another don't seem anything like the BCS picture. In some cases, the differences from the BCS picture are relatively small. In other cases, there seems to be no resemblance whatever. So I would basically like to tell you about some of these new superconductors, and in particular to ask, how do we actually tell whether we have a traditional BCS type superconductor or something more exotic? And that I think in itself is quite an interesting story. Okay, so let me go to the next slide, please. Okay, this table may look rather frightening. Across the top, I've listed some of the classes of superconductors which we now have. I start with the classic superconductors, and these are basically the ones that we knew about up to 1975. So typically things like aluminum, tin, lead, and that sort of thing. In the next column, I've put a couple of superconductors which were discovered after 1975, but still well within the 20th century. BKBO, that's barium, potassium bismuth oxide, and magnesium diboride. The next class is the heavy fermion superconductors, which were first discovered in, I think that was 1975, yes. They were the first class of exotic superconductors to be discovered. Then we have a large class of organic superconductors. There are the ruthenides. There aren't too many of those, but they are rather interesting. We have the fullerenes, carbon-60 and so forth. We have the ferropnictides, that's the iron-nitrogen type compounds. And finally, we have the cuprates, the so-called high-temperature superconductors. And then in the rest of this slide, I've listed various properties which are all possessed by the classic superconductors, and some of which at least are not possessed by the exotic ones. So the first property is actually that the transition temperature of the classic superconductors was always thought to be less than about 25 degrees absolute. Now, in fact, when I originally wrote this graph, this was true, but subsequently I had to put a brackets around the tick there, because in fact, in the last few years, we have actually discovered a class of superconductors, the so-called metallic hydrides, which seem to be classic superconductors, and they have really enormous transition temperatures, pretty much nowadays room temperature. So that was very unexpected. Apart from that, the classic superconductors do all have transition temperatures below about 25K. The classic superconductors have a Fermi-liquid normal state. They have, as far as we know, no phase transitions other than the superconducting one in the relevant part of the phase diagram. The order parameter is believed to be a simple S wave. The mechanism is, according to BCS, is the exchange of virtual phonons. The crystal structure is relatively simple, and they are stoichiometry insensitive. That is, it doesn't matter. It usually doesn't matter too much whether you put the odd impurity in there. It doesn't affect the superconductivity very much. Well, as we'll see, the exotic superconductors, each of the subsequent columns has a cross in at least one place. So that at least in one respect, each of these exotic superconductors, it is not similar to the classic ones. But you might ask, how do we know? Well, obviously, properties 1, TC less than 25K, 3, no neighboring phase transition, 6, which is the crystal structure is simple, and 7, stoichiometry insensitive. All those you can read off quite directly from the experiment without any great problem. As to 2, that they have a Fermi-liquid, the classic superconductors have a the Fermi-liquid normal state. That's not quite so straightforward, but for example, you can usually read that off from the temperature dependence of the resistance. Generally speaking, the classic superconductors have a typical so-called block Gruneisen form of the resistance as a function of temperature. But then the most intriguing differences are differences 4 and 5. That is, that the order parameter may not be S-wave, and that you may not have a phonon mechanism. And it's mostly those that I'm going to be discussing in this talk. But let me just emphasize before I go on that each of the exotic superconductors, that is anything but the first column here, does indeed have at least one property which is different from those of the classic superconductors. And in the case of the cuprates, they actually have none of the properties of the classic superconductors. So they really are very different indeed from the classic superconductors. Okay, but let's go on and ask, how do we tell, first of all, whether we have a phonon mechanism, and secondly, whether the order parameter is S-wave. The next slide, please. Okay, so first of all, let's consider the question of a phonon versus a non-phonon mechanism. Well, you remember that the original prediction of BCS was that the transition temperature to the superconducting state was twice the Debye frequency times this exponential factor. Now, it's usually this exponential factor which is the most important, because that can vary a lot between one superconductor and the next. But in the present context, the important point is that both the quantities n of 0, that's the density of states at the thermal surface, and the effective attraction, neither of those depends on the isotopic mass of the substance you're talking about. The only dependence on the isotopic mass comes through the Debye frequency, which is proportional to the mass to the minus a half. So within BCS theory, if we predict that if superconductors which are chemically identical but have different isotopic masses, if they are compared, then you should find that the transition temperature is proportional to the isotopic mass to the power minus alpha, where alpha in fact is a half. It's convenient to just make it a little more general. Now that prediction is in fact satisfied by most classic superconductors. For example, aluminum, tin, and lead. There are a few exceptions, but generally speaking, they can be understood by a more sophisticated theory, which was originally due to Bill McMillan, who was, again, a former colleague of mine here at the University of Illinois. He took into account not just the exchange of phonons, which gives their attraction, but also the Coulomb interaction between electrons, which gives the repulsion. And he deduced that in general, the isotope exponent, alpha, should be a half of 1 minus A, where the quantity A is always greater than 0, but may be greater than 1. So that in principle, at least, the isotope exponent could be negative. And this prediction does seem to be borne out in the sense that no examples are known of a classic superconductor which has isotope exponent greater than a half. So, moreover, this suggests that if you were to find alpha about 0, so somewhere close to 0, then that would suggest, well, it wouldn't prove that you might have a non-phonon mechanism. Let's say, it doesn't prove it because within the Macmillan theory, alpha could be 0, but it takes quite a bit of work to get it to be 0. So generally speaking, if you have a small isotope exponent close to 0, which is the case, for example, in the cuprates, that will suggest a non-phonon mechanism. Nevertheless, all the evidence that is from, say, flux quantization, the Josephson effect, and so on, suggests that even in exotic superconductivity, the basic principle is still Cooper pairing. Well, if phonons don't play a role, then the only origin of Cooper pairing has to be all electronic. That is, you have to have a Coulomb mechanism for forming the pairs. Next slide, please. Yeah, but the Coulomb interaction, even when it's screened, is intrinsically repulsive. So if I write down my the Hamiltonian, which I think describes the conduction of electrons in a metal which may become superconducting, consists of two parts. There's an H0, which consists of the kinetic energy plus the potential of the static lattice, the ions, plus a potential energy, which is just the Coulomb interaction between the electrons. Now, if the system is going to make a transition at low temperatures from the normal state to the superconducting state, then prima facie, there are only two possibilities. You have to reduce the expectation value of the total Hamiltonian. So you might reduce the expectation value of H0, or you might reduce the expectation value of the interaction V. Now, if you're going to reduce H0, that means that it must have already been in the normal state, which we think of, at first sight at least, as a simple Fermi C, that it must be considerably greater than the non-interacting electron value. Which in turn means that our assumption that it's a simple Fermi C has to be in one way or another wrong. That's one possibility. The second option is that the Coulomb interaction is already large in the normal state, and that by forming Cooper pairs, we reduce that Coulomb interaction. So whichever of these options is true, this implies then that exotic superconductivity, that is non-phonon superconductivity, must imply a strongly correlated normal state, which is why the field of exotic superconductivity is sometimes called by another name, strongly correlated electron systems. There's sort of a historical reason for that, which I won't go into, but crudely speaking, the phrase strongly correlated electron systems mostly refers to exotic superconductivity, although it can include some other things as well. Okay, next slide, please. Okay, most of this talk, however, is going to be about how we find out about the symmetry of the order parameter. You recall that the order parameter, as I explained in the last lecture, is essentially the relative, or well, it is the wave function of the Cooper pairs. And generally speaking, if your center of mass is at rest and you fix the spins, then the quantity f sub k, which is the pair wave function in k space, that is just essentially the wave function of the Cooper pairs. And now you remember that, just go back a moment to the top of the slide. You remember that in BCS theory, the general form of the zero temperature gap equation is that first equation, very familiar one, except that there is actually, I'm afraid, a typographical error. That little epsilon k at the end should be a capital EK, where EK is the usual BCS excitation energy. It's the square root of epsilon k squared of delta plus delta squared. So sorry about that. Well, if the potential VKK prime is a constant, as BCS took it to be, then the solution of that equation is simply that delta sub k is a constant, and that in turn implies that f sub k, the order parameter in k space, is simply a function of the direction of k on the Fermi surface. I'm sorry, I said that wrong. It's not a function of the direction, it's just a function of the magnitude of k. So it's independent of the direction of k on the Fermi surface. And then, as I mentioned in the last lecture, the real space form of the pair wave function is given by this rather lengthy expression here, which the important point to notice is that that is merely a function of the relative direction of the two electrons. Sorry, what I did, it's a function only of the magnitude of the separation. It's independent of the directions. Another way of putting that conclusion is that the pairs form in a spin singlet state with relative angular momentum 0. And a state with relative angular momentum 0 is usually called an S state. Okay, next slide, please. If B is not constant, but nevertheless is slowly varying when K varies over a range of the order of Kf, then that result still holds. And crudely speaking, we believe that that is true for just about all the classic superconductors. However, if V varies substantially on a scale less than Kf, as it does, for example, in liquid helium-3, then delta K, the gap, and hence the pair wave function, f sub k, can be anisotropic. In other words, delta of k is a function, is now a function of the direction k, as well as the magnitude, and f of r is a function of the direction of r. And moreover, the spin state is not necessarily single. And those statements remain true even when most of BCS theory is inapplicable. So generally speaking, we call a superconductor with pairing different from simple S wave exotic, and those systems are usually more interesting than S wave. Incidentally, you'll notice that I have in fact been a bit inconsistent here. I've used the word exotic in two rather different senses, but they usually go together. Generally speaking, we find that superconductors which don't have a phonon mechanism also don't have an S-wave order parameter, and vice versa. It's not universally true, but it's usually true. Okay, so let's just go into the symmetry of the order parameter a bit more in a bit more detail. If we neglect the crystal lattice and spin orbit coupling, then the Hamiltonian or free energy should be invariant separately under spatial rotations and spin rotations. They're essentially independent. And therefore, both the total spin S and the total internal angular momentum L of the pairs are good quantum numbers. Now, since you only have two electrons forming your pair, and each of them has a spin of half, the only possible values for the total spin are 0 and 1. But the relative orbital angular momentum can be 0, 1, 2, 3, essentially any integer. And I shall go back at this point to calling that relative orbital angular momentum script L, little l. However, there is a constraint which has to be satisfied. According to the Pauli principle, then S equals 0, that is a spin singlet state, has to be associated with even values of the orbital angular momentum, 0, t, 4, whatever. While s equals 1 has to be associated with odd L, 1, 3, or 5, whatever. And actually, that's not strictly speaking universally true. It's only true so long as the two electrons never occupy the same space, the same point in space at the same time. I'm sorry, as long as, I seem to be saying things wrong here. It's true so long as there is a non-zero amplitude for the two electrons forming the pair to be at the same place at the same time. If that's not true, and in certain very crazy theories of superconductivity is not true, then you can actually violate the Pauli principle. But that's a whole topic in its own right, which I won't try to go into. Most people think that particular complication is not really relevant to the superconductors I'm going to discuss, but who knows, it might be. But for now on, I'm going to assume that the Pauli principle does hold. Next slide, please. Even with these assignments, there are different possibilities. And in fact, in the last lecture, I talked about one of them, liquid helium-3. In liquid helium-3, both the A and the B phases have total spin and total relative orbital angular momentum 1, but the A phase, with some convenient choice of axes, has SZ equals 0 and LZ equal to 1, whereas the B phase, in the absence of spin-orbit coupling, has S equal 1, L equals 1, but they're coupled in such a way that the total orbital, the total angular momentum, the sum of the orbital and spin angular momentums, J, is 0. That's true if you don't take spin-orbit coupling into account, but as I mentioned in the last lecture, if you do take it into account, you get this funny rotation of 104 degrees. That's more complicated. Well, I don't want to talk any more about helium-3 in this lecture. That's just to remind you that that is a case where you have an isotropic pairing. Let's rather talk about the real-life exotic superconductors. In those, these symmetry considerations tend to be modified for two reasons. First of all, many of the exotic superconductors are quasi-two-dimensional. That is, they tend to consist of well-separated planes, like, for example, the copper oxide planes and the cuprate superconductors. And therefore, the symmetry of the order parameter is defined only within the plane, which actually makes life rather simpler. The second point is that the original O3 or O2 symmetry is broken by the crystalline lattice. For example, in a square lattice, you find that instead of O3 symmetry, which would be the symmetry for free space, you get a D4, the so-called D4 symmetry, which is basically the symmetry of the square. So it contains only the only symmetry operations it contains are reflections and pi/2 rotations. So, as I say, many of the exotic superconductors are nearly two-dimensional and do have a square lattice. Those include strontium ruthenate, the cuprates, the ferroclinides, and some others. And so you do actually have this D4 symmetry. And what then are the possible symmetries of the order parameter? Okay, let me just sort of make that distinction a little more clearly. The Hamiltonian, or the free energy, has the D4 symmetry, the symmetry of the square. However, the order parameter may break that symmetry, and in fact is believed to do so in many cases. So here are some possibilities. The most obvious and in some sense most boring case is that you have an S wave. That is, although your pair wave function is not exactly circularly symmetric, it nevertheless is positive all the way around the Fermi surface. So you get pluses on all the quasi-lobes. A second case is the so-called P plus IP symmetry. In that case, it's rather interesting. You get a, you can see this. The lobes have a plus for the north, what you might call the north lobe, and I for the east lobe. And I don't know if you can see there's a minus sign for that's -1 for the south lobe and -I for the west lobe. The third possibility is that you have a D-wave-like symmetry where you have pluses on the north and south lobes and minuses on the east-west lobes. And those three respectively correspond roughly. They sort of the analogues for a square lattice of the L equals 0, L equals 1, and L equals 2 order parameters in free space. Next slide, please. So now I think an interesting question which I want to spend some time on is how do we tell which of these possibilities is realized? Well, one rather simple consideration is that the spin susceptibility chi should tell you whether you have S equals 0, that is a singlet, or and therefore L equals even by the Pauli principle, or the opposite. Indeed, we have a singlet, so that L is even. Then in the superconducting state, the susceptibility is reduced. And the reason for that is that if you apply a magnetic field and try to polarize your system, you have to break up the Cooper pairs. And in fact, you have to distort them as shown in the diagram. You have to distort them so that, say, the upspin Fermi surface is larger than the downspin Fermi surface. And the Cooper pairs don't like that at all. And generally speaking, if that happens, they won't form. So, so what happens, in fact, is that the Cooper pairs, as it were, stay as they were. They keep the two Fermi surfaces the same, but then you get no polarization. So susceptibility is reduced. And that's indeed what is found in classic superconductors. For the for S equals 1 pairing, it's a little more complicated. If SZ is equal to plus or minus 1, as it's believed to be in helium 3A, then in fact you can freely form. Now that's really what the diagram refers to here. So in the diagram there, you've actually got upspins and downspins, each forming their own Cooper pairs independently. And in that case, it doesn't matter whether the Fermi surfaces are the same or not. The system simply doesn't notice. In other words, your susceptibility in the superconducting state is simply the same as the susceptibility in the normal state. If you had, say, the B phase of helium-3, life gets a little more complicated. Some of the pairs, as it were, look like singlets and some look like triplets. And so you've got a reduced susceptibility, but it does not reduce to 0. That's point 1. Point 2 is that the S-wave state usually has a non-zero minimum value of its excitation energy, that is the energy gap. And therefore, as the temperature falls to 0, the number of normal excitations, the electrons which are not forming Cooper pairs, falls off exponentially as exponential minus delta over T, where delta is the minimum value of the gap. And that means that quantities like the electronic specific heat and so forth are exponentially small. By contrast, most exotic pairing states have nodes in their gap. That is, the energy gap will go to zero for some points on the Fermi surface. That means you have a substantial number of excitations as the temperature drops to zero, and therefore the specific heat and other quantities are proportional not to an exponential but to some power of T. And that's true, for example, for helium-3A. It does indeed have a power law specific heat in the zero temperature limit, not an exponential one. So that's a second consideration. A third consideration relates to the effect of non-magnetic impurities. For a simple S-wave state in free space, which is the case considered by BCS, the transition temperature is virtually unaffected by putting in impurities, non-magnetic impurities. Indeed, some of the best, that is the highest temperature, BCS superconductors are really quite dirty alloys, in fact. So alloying just doesn't hurt superconductivity much, provided that you have a simple S-wave state. If the S-wave state occurs in a lattice, then it's not exactly spherically symmetric, but it's still non-zero everywhere, and so you expect some depression of TC, but not to zero. However, if you have an exotic state, like a P wave or a D wave-like state, then non-magnetic impurities have an effect which is qualitatively similar to what magnetic impurities have in BCS. Now, we haven't actually talked about that, but what happens in BCS theory, if you put in magnetic impurities, is they have a big effect. You find that the transition temperature goes to zero as soon as the relevant scattering rate becomes comparable to the root mean square gap for the pure case. This is believed to be the case also for non-magnetic impurities in an exotic state. And so, for example, it was found that in strontium ruthenate, a very small concentration of non-magnetic impurities is enough to drive the transition temperature to zero. And that's then usually taken, or was usually taken, as evidence for exotic pairing. I say was because until recently, that the idea that strontium ruthenate was exotic seemed to be relatively well confirmed by the experimental evidence. However, a recent experiment has actually shown that, this is an experiment at UCLA, it's shown that the spin susceptibility actually does fall off to zero as you go into the superconducting state. And that then is not compatible with having an odd parity state, that is S equals 1, L equals 1, say, which is what it was formerly thought to be. So that's a mystery, and it's still being debated. Okay, next slide, please. Okay, the technique I want to talk about finally is one I would like to speak a bit about this because first of all, it's a set of experiments in which I have myself been involved, and secondly, I think myself that it is the most convincing way of establishing the symmetry of the order parameter. All the previous things I've mentioned, the fact that the considerations involving the spin susceptibility and involving the low temperature thermodynamics and so forth, they will tell you about the magnitude of the order parameter, whether it goes to zero or not. They won't tell you about the phase or the sign of the order parameter. And to distinguish, say, a very anisotropic S state from a D state, it's not enough to know about the amplitude. the magnitude, you've got to know about the relative phase of the various lobes. So this experiment the experiment I'm going to talk about was actually proposed way back sometime in the 80s, I think, maybe in the 70s, but certainly proposed by Geschkenbein and Larkin in the context of the heavy fermion superconductors. No one, as far as I know, at least until relatively recently, ever tried that experiment on any heavy fermion superconductor, and it is in fact would be very difficult to do that for various reasons. However, in the early 1990s, people were most interested in the symmetry of the cuprate order parameter. And so I and various other people independently proposed an experiment which is actually like I didn't know at the time about the Geschkenbein-Larkin experiment. I found out soon afterwards, but and I don't know whether the other people who thought of this did or not. But anyway, we did come up with this. What you do is to take a sample of the material you're interested in this case it would be YBCO, yttrium barium copper oxide, a famous cuprate superconductor, and you connect it to an outside superconductor, which is something like lead, something you're pretty confident you know about, through two Josephson junctions. So you make a circuit like the one on the top left. And we can do a similar thing, and this was eventually done by Ying Liu and his group at Penn State for strontium luthenate to establish whether that was a p-wave superconductor or not. But you see in the diagram on the right, the two Josephson junctions are stuck on opposite faces, whereas on the one on the left, which is the one for YBCO, the Josephson junctions are stuck on mutually perpendicular faces. Now, why does this experiment informative? Well, the general principle is that the total effective flux trapped in the loop must be equal to the sum of the phase drops, delta phi, going across the different, going around the circuit. Now, part of those phase drops are, as it were, well known. They're due to the Josephson junctions involved. And they would happen just in any ordinary S-wave circuit, and the theory of that is well known. But the interesting thing about this particular setup is that the delta phi i's also include an internal phase drop due to the rotation of the pair wave function between the two Josephson junctions. So you see, if you do the YBCO experiment, in other words, you put your two junctions on perpendicular faces of the sample, then you see that the order parameter, which as it were is next to these junctions, has the same sign. So there's no internal phase drop. And the total flux in that case will be just equal to the phase drops across the two junctions. However, if the order parameter is D-wave, and in the early 90s it was thought that that was a plausible possibility for the cuprates, then what you find is that the order parameter changes sign as I go internally in the YBCO from one junction to the next. So that gives you an extra factor of pi coming into the expression for the total flux. Similarly, this is just an aside, but if you were to do the experiment indicated in the top right for strontium luthenate, say, and if it had a P plus IP order parameter, you get a plus on the top and a minus on the bottom. So again, you get a pi phase drop across the sample. Okay, so how do you see this? Next slide, please. Well, it turns out, again, this is a fairly simple piece of analysis, gives you this. In the S-wave case, the phase drops across the two Josephson junctions by themselves just tells you that, some of those phase drops is equal to total flux. And that then implies, that is not immediately obvious, but it's a simple calculation to show, that means that the critical current of your circuit, that is the maximum current you can get to flow through it without dissipation, that occurs when, sorry, there's another typo here. This should be, in the first line, it should be n phi 0, not n plus a half. So phi is n times phi 0. And that's what indeed found in all sorts of circuits made out of ordinary superconductors, where no one doubts that it's all S-wave. So that's a very standard result. The new result is that for a D-wave, the sum of the phase drops across the junctions themselves is equal to not the total flux, but the total flux plus pi. That then means, in turn, that you get a maximum of the critical current at n plus a half phi 0. Now, by now, so this is really a rather direct way of measuring not the amplitude of the order parameter, but the relative phase as you go around the Fermi surface. Those experiments were first done by my colleague Delvin Harlinger here at Illinois for the cuprates in 1993. And this is very soon followed by other groups. For strontium ruthenate, the experiments were first done somewhat later, around 2000, by Ying Liu and his group at Penn State University. And people have also done experiments for the ferroclictides, doing experiments of this general type. And the conclusions seem to be the following. For the cuprates, it seems that these experiments, at least as they stand, do seem to establish fairly unambiguously that the order parameter is D-wave in nature. And this would, in fact, if true, this would be the first example of a superconductor with D-wave order parameter. I should just say, as a matter of completeness, that there is there's a small group of people, maybe only one or two, I suspect nowadays, who claim that the cuprates really are S-wave and these experiments are somehow misleading. But I think the vast majority of the community is convinced that they are reliable and that indeed the cuprates are D-wave. Let me just go to the ferroclictides next. The ferroclictides turn out to be very complicated because they have all sorts of different bands which intersect the Fermi surface. The usual belief, although it's not 100% sure, is that they actually have an S-wave order parameter, but it's of a rather complicated type. It's not just a simple one like in the original BCS theory. The most intriguing case is strontium ruthenate. For many years, it was thought, first of all, that the spin susceptibility remained constant as I went into the superconducting phase. Now, you remember that if that's true, that has to mean that the pairing is spin triplet, S equals 1, and that in turn means that the value of the orbital angular momentum is odd, most likely 1. Moreover, the Josephson experiments, which Ying Liu and company did at Penn State in the early 2000s, seemed to show that the situation was similar to the cuprates. In other words, the maximum of the critical current did not occur at 0 flux, but at half a flux quantum. that then would be consistent with P plus IP form of pairing. And there are other more complicated features of that experiment, which I won't go into, which do seem to indicate rather unambiguously there's P plus IP. Unfortunately, so for 20 years or so, from roughly 2000 to 2019 or 2020, everyone believed, or practically everyone believed, that strontium ruthenate was P-wave. And that was actually very interesting because it would have meant that it could possibly be used for topologically protected quantum computing. However, unfortunately, in 2019, I think now, there was this experiment at Los Angeles, UCLA, which showed that indeed the spin susceptibility dropped as you went into the superconducting phase, which then would indicate fairly unambiguously that the spins appeared in a singlet state. So we now seem to have a contradiction. The susceptibility experiments say that it has to be spin singlet. The Josephson experiments indicate rather strongly that it has to be not only spin triplet, but a particular type of spin triplet, namely P plus IP. And at least to my knowledge, to date, the only way that people have been able to reconcile these two apparently mutually contradictory results is simply to claim that one or other of the sets of experiments is wrong. And so there has been a certain amount of an argument claiming that the Josephson experiments are wrong. So they certainly, it'd be a good thing if people can go and redo those. And similarly, if other groups several other groups can reproduce the spin susceptibility experiment. But right now, we do seem to have a contradiction. Well, roughly that's what I wanted to say. There are lots and lots more things that one could say about exotic superconductivity and the ways in which it might perhaps be used, for example, for topological quantum computing. But I see my time has run out, so I'll stop at this point. Thank you.
Okay, thank you, Professor. So let's open for questions. So do we have any question in the audience? Yes, Vanderlei?
Hi, Professor Leggett. Thank you very much for the nice presentation. I have a curiosity that you did not touch in your presentation. You said something about impurities, right? And we know that in traditional superconductors, sometimes impurity break down the longer range of superconductivity and make small domains of superconductivity. In those materials, which are solids, and normally they are filled with defects, it is natural in those, as you said, exotic superconductors, we have domains of superconductivity instead of, the whole material be a superconductor.
Okay. Now, when you say that you form domains, are you talking about what is normally called the intermediate state? That is a state in which you have reasonably macroscopic amounts of the superconductor becoming normal? Or are you rather thinking about what's usually called the mixed state, in which you have a large number of vortices formed? Which of those did you mean?
Yeah, but you know that those impurities, they seems to be a problem for the long range superconductivity, right?
Well, I think the standard argument would say that you start off with this pair radius, the coherence length, as it's often called, which is very large, something of the order of 10 to the fourth angstroms, so forth. And the effect of alloying with non-magnetic impurities can be to drastically reduce that pair radius. So the effective radius of your pair is now much less than 10 to the 4 angstroms. The effect of this would normally be to take you from a so-called type 1 to a type 2 superconductor. And in the very, as you know, in the very simplest geometries, if you put a type 1 superconductor in a magnetic field, then either it's superconducting or it's just all normal. There's no mixed state formed. But in a type 2 superconductor, you will get the magnetic field punching through in the form of vortices, and so it will be inhomogeneous. I'm not entirely clear whether that's what you're referring to when you say that the effect of impurities is to give you regions of superconductor.
Okay, well, thank you.
Okay.
Thank you, Dr. Leggett, for your talk. My question is, how far are we from having superconductors integrated into the power transmission, like in the country's infrastructure?
Oh, yeah.
Yeah.
Oh, okay, that's a very interesting question. I mean, I'm not an expert on this area of applied superconductivity, but well, I can say, first of all, there is a very small part of, I think it's the Brooklyn area of New York. It might be the Bronx, but I think it's Brooklyn. A very small area, about 1 mile square or so, of housing in New York City, which actually get their electrical power through, of course, standard cables, but the last mile of the cable is in fact a superconductor. And of course it has to be kept very cold and so forth, but that's just a sort of experimental demonstration that you can in fact use superconductors for long distance power transmission. The downside, of course, is that right now these superconductor cables are so expensive to make that it certainly would not be economical to put the whole of the, say, the US or the Brazilian grid on high temperature superconductivity. But as to that, I mean, I think it's anyone's guess whether this will ever happen, and if so, how soon it will happen. My own guess is yes, it probably will happen, and maybe might even happen perhaps within your lifetime. I suspect not within my lifetime, but perhaps within yours. But however, there's another application which is much more short term. And again, I don't know much about the details of this, but apparently there is in the US, there are 3 different power grids which cover different regions of the country, and they all come together at a certain point in northern Texas. And if there is a serious problem with one of the grids, then it's possible to, as it were, switch the power over into the other networks. And right now, this is being done by a conventional switching mechanism, but I believe that there is a plan to replace that by a superconducting switching mechanism. And this has the enormous advantage that this is a sort of automatic fuse. In other words, if you, as you know, a fuse is just a device which ensures that if the current in a particular circuit exceeds a certain dangerous value, then you shut the current off. Now, one of the nice things about superconductors is that the moment they can carry a certain amount of current. The moment you try to put more than that amount of current through them, they will immediately switch into the normal state and become highly resistive. So in other words, this is a perfect, as it were, a perfectly natural fuse. And I believe that this is what's going to be used in this switching station in northern Texas and perhaps elsewhere, what I know. So there certainly are some applications which are happening right now. And as I say, I think my bet would be that the others are going to happen in 20 or 30 years.
Thank you for your answer.
So, Professor, we also have a question from YouTube, from Jacopo D'Aberto, and he says, thank you, Professor. What are, according to you, the future perspectives for condensed matter theory?
Oh boy.
Big question.
I think the most interesting, I mean, I'm sure that there's a fair amount of condensed matter theory which is sufficiently closely tied to applications, and rather sometimes conventional applications, that people will still be spending time on it. So, for example, I suspect that people are still going to be, say, calculating band structures for exotic types of substance for many years to come. But that's probably not the most interesting part. I think probably the most interesting part of condensed matter theory in future is going to be the applications to other areas of science, which apparently, at first sight at least, have nothing to do with condensed matter physics. One rather amusing example, which you might know about, is bird flocking. That is the way in which flocks of birds form and rearrange themselves and so forth. It turns out that in some sense this is really rather like a problem in certain kinds of atomic gases and so forth. And so people have used their knowledge of physics to address this kind of problem. And there are many other applications of this type, I think, which we're going to see more of in future years. But I think in some ways the most fascinating possibility is that we will actually discover some genuinely new phase of matter. New in the sense that superconductivity itself was new when it was discovered in 1911. And that this will actually bring in, as it were, aspects of possibilities for the many-body wave function, which previously had simply not been thought of previously. So we have, superconductivity is not the only example of this happening in the past. Another good example is the fractional quantum Hall effect. And I think it's very likely that there will be more and more things of this nature coming up. We're now able to go to temperatures which are something like a factor of 10 to the 4, probably much more than that actually, more like 10 to the 9. The temperatures which you can go to now on a logarithmic scale are now down by a factor of 10 to the 9 from what we could do when I was a student. The kinds of pressures we can apply, the kinds of accuracy we have in various, say, photo detection devices and so forth. So we're always improving our ability to get colder, to go to higher pressures, to measure more accurately. And I think the odds certainly are that we'll find at least one, probably more than one, really exotic phase of matter that we've not previously thought about. But obviously I can't tell you what that is, or I would have thought about it.
Okay, thank you. Any other question? No? If no, before thanking Professor Leggett again, I wanted to ask you a favor, Professor. Could you just go more into the light so we can take a picture with you?
But sorry, do what?
Could you go a little bit behind to have a little more light on your face? Because
yes,
from
actually,
here we
probably
cannot
it's
really
easier to just adjust
you.
my camera.
Ah, yes.
How's that?
Yes, thank you. So we can take a picture of you. Okay, so we are going, okay, just a minute. Okay, so we are going to take the picture
So should I say
right
cheese?
now.
Cheese.
Yeah, I smile. So yeah, we did it. So thank you very much, Professor Leggett. It was a very nice lecture, and we want to thank you again. So thank you.
That's good.
Thank you.
Okay. So,
Bye.
bye-bye. Bye-bye.
Como eu falei que ele iria fazer. Mas thank you.
Okay.
Hello, Professor Luca Galantucci. Can you hear us?
Yes, can you hear me?
Yes, perfect. Okay.
Okay.
Next speaker is Luca Galantucci from Newcastle University. I will give you a brief introduction. Professor Luca Galantucci did his PhD at University of Milan under the supervision of Professor Maurizio Quadri. He did postdoc at Polytechnic University of Milan, University of L'Aquila, and Newcastle University, where currently he's working. The topics of his research work are quantum fluids, superfluidity, atomic physics, and turbulence. And for today, the topic of this talk is friction-enhanced lifetime of bonding quantum vortices. So please, Professor, you have the microphone now.
Okay, so thank you very much for the introduction. And firstly, let me really thank the organizers for organizing this conference in these challenging times. I mean, it was a great bet that you did in trying to organize this conference. And I think it was a challenge that you have definitely won. And then also thanks also for giving me the opportunity to present recent work on collective effects in superfluid helium. So the aim today, my aim is to try to convince you that the answer to this question is yes. So superfluid helium can be described actually is an active fluid, whereas as active fluid, I mean multi-phase flows where you have a large number of active agents which interact directly, but which mainly interact indirectly by hydrodynamical interaction. So for example, fungal spores dispersed in air, bacteria diluted in aqueous suspensions, or particle trapped in optical vortices, or even like a cyclist drafting in a peloton. So first of all, I would like to thank the collaborators of mine, which with whom I realized this work. So Carlo Barenghi and Andrew Bagley for Newcastle University, and Giorgio Krustolovic from Observatoire de la Côte d'Azur in Nice in France. So what I'm going to present today is included in two recent papers, one of which published now 2 years ago, and one which is on archive and is currently under review. So this is the outline of my talk, and so the central part of this talk will be focused on the modeling of the mutual friction force between quantized vortices and thermal excitation, which make up the normal part of helium. And so, but before I would start with a very brief introduction to superfluid helium, and especially on the parts of the characteristic of superfluid helium, which will be important for this talk. So, I mean, as you well know, this is the phase diagram of helium-4. And so the important thing is that there are two liquid phases. One, let's say, high temperature liquid phase, so above 2.17 Kelvin, and this is more or less an ordinary Navier-Stokes viscous fluid, classical fluid, with very low values of density and viscosity. If we decrease the temperature below this lambda line, which is a line where we observe a second order phase transition, then this liquid phase becomes superfluid, and this is precisely this liquid phase that we are going to look at. And superfluid helium, according to the two-fluid model elaborated independently by Thies and Landau between the 30s and the 40s of the last century, can be described as an intimate mixture of compenetrating and inseparable fluids. So the superfluid component and the normal fluid component. The superfluid component is loosely related to the condensate fraction. So it's related to the phenomenon of Bose-Einstein condensation, even if not exactly like this, because superfluid helium is not a weakly interacting Bose gas, but is a strongly interacting liquid, while the normal fluid is a fluid constituted by thermal excitations, so phonons and protons. And in the temperature range which we are interested in, we will be mostly talking about protons. So we will be interested in temperature around 1.95 Kelvin. So each of those components has its own density field and its own velocity field, meaning that simultaneously in each point locally you have two different motions, and so the superfluid motion indicated with Vs and the normal fluid velocity indicated with Vn. So the superfluid component carries no entropy and it has no viscosity, while the normal fluid is the only part which carries entropy, hence heat, and has very low viscosity, but is different from zero. So this viscosity is more or less 100 times more than the viscosity of air. So actually, the superfluid component can be more or less described as an Euler fluid, while the normal fluid can be described like an ordinary classical viscous Navier-Stokes fluid. So here we have a diagram of the density fraction of the superfluid component. So it's the first curve, and the normal fluid fraction, which is the lower curve. And we see that while at very low temperatures the superfluid is entirely the superfluid helium is entirely superfluid, while at 2.7 Kelvin the helium-2 is completely normal fluid. And let's say that there is this region where the superfluid fraction collapses and the normal fluid fraction increases, and around 1.95, 1.96 Kelvin we have the two density ratio are equal. And interestingly, in all this range between temperature range between 0 and 2.17 Kelvin, the overall density, so the sum of the two density, is constant. So actually, these two phases, they do not interact. So if the velocity difference between the two phases is sufficiently low, or if there is no rotation, or if the cooling of the superfluid is done very, very slowly. However, if on the opposite we have some inflation of quantized vortices, then those two, as we will see, those two phases will actually interact, and interaction is very important, especially for the purpose of this talk. So as you well know, also like in Bose-Einstein condensate, quantized vortices are topological defects of the superfluid fraction. They cannot very effectively be described as one-dimensional structures, so one-dimensional curves in a two-dimensional space. And the difference with between helium and Bose-Einstein condensate is that the core size of these vortices is much smaller, so it's of atomic size. And this is there is a very large separation of scales between the core size of the vortices and the average intervortex distance L, which I've indicated with L, and the size of the typical systems that, for example, are used in experiments. I will come back to this large separation of scales in the next slide, but let me first say that, very importantly, the superfluid vorticity, because of quantum mechanical constraint, is confined to these vortex lines. So the superfluid vorticity is a singular delta distribution, and around each of these quantized vortices, the circulation is quantized in terms of the quantum circulation K, which is the ratio between the Planck constant and the mass of the helium atom. So consequently, the superfluid velocity is given by an integral, the Biot-Savary integral over the whole tangle, which is the superfluid velocity field produced by the tangle of vortices, and any other potential flow which is determined by the macroscopic boundary condition. Very importantly, this vortex line acts as scattering center for the thermal excitation which compose the normal fluid, and therefore there is a momentum exchange between the vortices and the normal fluid, and therefore there is a mutual friction force between the superfluid component and the normal component. Just coming back to the length scale I was mentioning before, so this is the difference between superfluid helium you see here on top and the Bose-Einstein condensate you see here below. So there is a very large separation of scales between the size of the containers normally used in helium experiments and the average intervortex spacing and the core size, which I've indicated here with psi, while, so you can see them here, 10 to the 8 and 10 to the 3 respectively, while in BCs, more or less, the ratio between the size of the Bose-Einstein condensate and the heating length is smaller than 100. In this case, as the size of the Bose-Einstein condensate, for example, in a cigar-shaped condensate, I'll take the smallest size. And also, importantly, the average intervortex spacing is comparable to the size of the Bose-Einstein condensate. So actually, if we look at helium, we have that the ratio between the largest and the smallest scales is even higher than the one that we observe in classical turbulence, where here eta is the Kolmogorov viscous scale, so the scale with which viscous dissipation takes place. The fact that in helium we have access to a very large separation of scales means that in some conditions, so for example, if the helium is forced mechanically at large scales, if we probe the flow at length scale much larger than the average intervortex spacing L, we might see classical turbulent features emerging. So, for example, we have the same Kolmogorov turbulent kinetic energy spectrum, which scales at k to the minus 5/3, where k is the wave number. We observe the same turbulent decay of vorticity, and also the PDF of the probability density function of the velocity are Gaussian. However, if we probe the flow at length scales smaller than the average intervortex spacing, we might see some exclusively quantum behavior. So, for example, the PDFs now have power law tails, and also there is a claim, even if it's still debated in the community, that we have an enhanced intermittency. So intermittency is not more universal, but it's enhanced and depends in temperature. This is the claim in this physical review fluids paper, while some other very recent work by Nicolas Muller, Ignacio Polanco, and Giorgio Pustulovic showed that actually at t equals 0 with the Gross-Pitagoric equation, the intermittency in a Bose-Einstein condensate is identical to the intermittency in classical turbulence. So now I will go, after this introduction, I will just do a recap on the characteristic of the mutual friction force, which I've indicated with FNS, which is very important for the dynamics of the superfluid helium, which determines the dynamics of superfluid helium, depending on the different system we are investigating. So the first experimental work and the first theoretical modeling of the mutual friction works dates back to the pioneering work of Hollenbein in the late 50s, where they modeled and they also performed an experiments by investigating the famous rotating helium bucket. Since then, we have distinct approaches have been used to model the mutual friction force, and this depends on the probe length scales of the flow. So if we are in length scales much larger than the average intervortex spacing L or smaller than the average intervortex spacing L, the configuration of the superfluid vortex angle, and if some numerical simulation were performed, so depending on which simulation, you would adopt one or other models. So the models can be subdivided loosely in three categories. So the first is what Hollenbein used to model the helium, the rotating helium bucket. And in this case, they focused on the mathematical expression of the mutual friction force, and they also determined the friction coefficients. And in this case, they focused the attention on a length scale, so let's say capital delta much larger than the average intervortex spacing, meaning that in that case, the representative volume element was threaded by many parallel vortex lines, because in fact, in this case, when you have a rotating helium bucket, you have that the vortex angle is in a very particular configuration. It's an array of straight vortices, which in fact here were imaged in 2006 by Greg Bewley and others, reported in Nature. So here you really see that in a rotating helium bucket, you have an array of rectilinear vortices. Then in the late 70s, Klaus Schwarz did the first numerical simulation of superfluid helium turbulence, and he introduced the so-called local kinematic model, and at length scales smaller than the average intervortex spacing L, which means that the vortices are discretized, as you can see here in the top right image. The vortex lines are discretized in a certain number of finite vortex elements. However, in this case, two big assumptions, two big approximations were made. So the first one is that the same friction coefficients which were determined by Hollenbein experimentally were used in this case, where, as you can see here on the right, the vortex angle is completely different from an array of straight vortices. So it's very complicated, and they assumed that the friction was the same. And the second was also that Schwarz didn't consider the retraction, so the back reaction of the moving superfluid vortices on the normal fluid. This meant that the normal fluid was not determined self-consistently, but was imposed a priori and dependent on the system that we were studying, so on the boundary conditions of the flow. The third is the so-called fully coupled local approach, and also in this case, the probe length scales were smaller than the average intervortex spacing L, but in this case, the back reaction, so the mutual friction that the superfluid vortices exerted on the normal fluid was taken into account. So the two fluids, so so let's say that the superfluid vortex angle and the normal fluid velocity were evolved self-consistently, and this was done by the Newcastle group in the early 2000s, and I will come back to this later. While using the local kinematic approach, so the so-called vortex helium method by Schwarz, where you have an imposed normal fluid field, because the normal fluid velocity field, because there's this approximation that the vortices don't modify the normal fluid. Then imposing this normal fluid velocity field, it was possible to simulate the evolution of the vortex angle. Here with SI, I indicate the position of the ith vortex element. in which I've discretized the vortex tangle. And so you see several different normal fluid velocity field were imposed. So depending on the system that people wanted to investigate, and there was a lot of insight came from these numerical simulations. So for example, regarding counterflows or regarding where the two phases of helium flow in opposite direction due to thermal forcing, or so-called co-flows where the two fluids are forced in the same direction. We can see in some cases classical turbulence features emerging. Considering the fully coupled model, so which was elaborated in Newcastle at the early 2000, here, as said, we've got a self-consistent evolution of the normal fluid velocity field and the superfluid vortex tangle, because the neutral friction is taken into account in both the evolutions of the two quantities. However, in this case, what was necessary, it was to redetermine the friction coefficients, because of course in the helium in the Holbein rotating helium bucket was a coarse grain approach, and therefore the normal fluid was averaged on those volume elements of size delta much larger than the average intervortex spacing. While in this case, the normal fluid velocity field varies very rapidly with the position with respect to space at length scales smaller than the average intervortex spacing. So they had to recalculate these friction coefficients. This fully coupled model was used for example, the numerical simulation of a superfluid vortex ring placed initially in a quiescent normal fluid. So what happens is that the vortex ring travels because of the friction. It create normal fluid entropy structure. So these two normal fluid rings, one is in front, the blue one is in front of the superfluid vortex ring, the red one is just behind. The superfluid vortex ring is hidden by the biggest normal fluid structure here. And by exciting the normal fluid, it loses energy, so it shrinks, it accelerates, and then vanishes. So this is the behavior of a single vortex ring, which will be important also for later. So a single vortex ring, because of the friction, will shrink. Then also it was here on the right, you see a numerical simulation done by the same group, where you have a single vortex line which is perpendicular to the plane here. Shown here on the slide, and it's this red dot which moves towards the right and creates a dipolar structure of the normal fluid vorticity. So it's like when you have a stick and then you drive it into the water, and you would see those two vortex dipoles. However, there are some shortcomings for this fully coupled model, which was elaborated before. So it was true that the vortex, the friction coefficients determined by Hall and Vinyl, and therefore the problem was that these coefficients still were based on the fact that on this coarse-grained approach. Then, as you've seen, the other problem was that this approach was either employed to describe simple vortex configurations, so a single vortex ring or a single vortex line, or decaying turbulent flows, which meaning that there was no statistical steady state was able to be reached, and therefore the statistics, for example, to compare the normal fluid turbulence with the classical turbulence couldn't be done, because you need to have a statistical steady state. But the main issue was the fact that the numerical architecture that we used was not didn't allow a very high level of parallelization. So the normal fluid was solved, the velocity field was solved on maximum 128 cube grid, while now, for example, classical turbulent numerical simulation go up to 16,000 cube. And also the number of vortex points were very low compared, the number of vortex points which made up the tangle were very low and didn't allow a lot of, didn't allow a wide range of scale, which we have seen is very large. So only a small range of scale could be simulated. So all of these shortcomings are the motivation for our work. So for the development of a new model of quantum turbulence at finite temperature. So this algorithm is his acronym is FOUCAULT, so fully coupled the local model of superfluid turbulence. And we reckon that it is a more realistic classical model of the mutual friction force, which is based on, but we built on the work by Kivotis appeared in Physical Review of Fluids in 2018. Also, the distribution of the force, which is delta supported on the vortex line, so it is exerted by the vortex line on the normal fluid only where the vortex lines are. You need to distribute it on the grid points where you solve the normal fluid velocity field. We will see that it is an issue, and it was done by using physically consistent classical model. And the third novelty of this algorithm that it allows a higher polarization computationally, so in order to solve a wider range of scales. So you see that in this, all these three novelties are linked with classical fluid dynamics. So the first two concern the modeling of the mutual friction force and its diffusion in space. And the third one is a numerical issue, but we know that classical turbulent numerical simulations are very high resolution. Therefore, what we are doing now is that we have used tools from classical turbulence to investigate quantum superfluid helium turbulent flows. And actually, all of our framework is classical in the sense that the only very important, of course, feature that we take from superfluid helium, which derives from its quantum nature, is the fact that the superfluid vorticity is confined to the vortex line. If for a moment you neglect that, you will see that the approach is completely classical. So first of all, to model the mutual friction force, we use a classical low Reynolds number fluid dynamical approach, according to which the force which vortex line exerts on the surrounding normal viscous fluid is identical from the mathematical point of view and also from the physical point of view, is identical to the force which an infinitely long solid cylinder exerts to a classical viscous flow. And to do this, why we've been able to use this framework is because the Reynolds numbers involved in a superfluid helium are very, very small. So you see here 10 to the minus 5, 10 to the minus 4. This is mainly because the core size is atomic. From the mathematical point of view, from the former point of view, the dissipative part of the mutual friction force is equivalent to the Stokes drag, and also the fact that the vortex locally can be assumed like a cylinder, because can be approximated like a cylinder, because the core size is much smaller than the radius of curvature of the superfluid vortex tangle. So according to this description, actually the expression of the mutual friction force is given in the mutual friction force per unit length. In this case, it is proportional to the velocity difference between the velocity of the quantized vortex lines, so the vortex elements, which is S dot, and the normal fluid velocity, and the constant here of proportionality is given by this low Reynolds number approach. And you can see that it depends on the Reynolds number of the normal fluid flow around around quantized vortices. Here gamma is the Eulor-Mascheroni constant. So by using this mutual friction force, you can see that we are able to derive the expression for the equation of motion of the vortex line elements. So here S dot is the velocity of each of the vortex line elements in which you discretize the tangle, and you see that we have those two friction coefficients, which are very different from the previous coefficients because they depend on this coefficient D. And actually these coefficients, beta and beta prime, only depend on temperature and pressure, which they define the ratio of the superfluid and normal fluid densities, and the ratio between the quantum circulation and the viscosity of the normal fluid and the Reynolds number. And you can see that all these three numbers are non-dimensional numbers, so it's also quite elegant in a certain sense. So this, so what we do is that we couple this equation of motion of the motion of the vortex elements with the Navier-Stokes equation, suitably modified to take into account this mutual friction force FNS, and there, of course, there is also the incompressibility condition. So the two fields. So in one is the position of the elements that constitute the quantized vortex angle, and the normal fluid velocity field. They evolve self-consistently. At this point, as a numerical person tries to do at least a numerical simulation, you're faced with an issue which seems to be only numeric, but which actually is reveals some underlying physics. So here, in the picture here in the figure, you see that on black, the black cube is the grid points on where you calculate the normal fluid, and in the blue you see the discretized vortex line. So in green here I've shown I've indicated the mutual friction force which the line element SI exerts to normal fluid. This force is as I said before, is also as a singular nature. So it lives on the quantized vortex line, and so when we have to find a way in which you distribute this force amongst the normal fluid, the grid points where you solve the normal fluids. And so this means that you have to introduce, you have to define a procedure to determine these weights W, which depend, of course, on which point of the grid points you're using. The sum, of course, of these weights has to be 1 because it has to be a conservative scheme. And therefore, you have different options, which are quite arbitrary. So you have nearest neighbor, so you distribute the force to the nearest of the grid points, 3-linear extrapolation, so a linear extrapolation. And then once you have extrapolated them, you might want to use some filtering, so a moving average filter or a Gaussian kernel. However, so we tried some different of these extrapolation filtering scheme. So we take a single quantized vortex swing, which is initially in a quiescent normal fluid, and we observe its dynamics. We just said it is a shrinking dynamics because it loses energy towards the normal fluid. But if we observe the dynamics, we see that the dynamics depend on which type of filtering you use, on which type of extrapolation you use. Of course, this is a spurious numerical effect. But the problem is that because until now this way of distributing this force was arbitrary, then the problem is that you're never sure that what you get is actually describes what actually is going on. So what we were looking for was something which was physically consistent, and this is a problem that that has been faced also by the active matter community, where you have like a large number of point-like agents which exerts a strongly localized force on the viscous fluid in which they are immersed. So, for example, you have particles that are used in particle image velocimetry or particle tracking velocimetry experiments, bacteria, swimmers. So how do you distribute this force? This was solved actually quite only recently by Paolo Gualtieri and Carlo Casciola's group in Italy, in Rome at Università La Sapienza. And without going into too much detail, even if it's very interesting, very elegant, the derivation, the procedure, the step, that the main parts of the derivation is as follows. So by observing that because those point-like agents are very small, the Reynolds number around the Reynolds number of the flow, the viscous fluid around those active agents is very small, as in our case. And therefore, they used the unsteady Stokes equation singularly forced, and to show that. So what happens is that when those active agents, point-like active agents, they move, they inject some very localized normal fluid vorticity. And this normal fluid vorticity is then diffused by viscosity to the viscosity equation. And actually, when those normal fluid vorticity structure, they diffuse to the smallest relevant length scales of the flow, which in this case is equilibrium in delta x, then it is included in the calculation. So actually what you get at the end of the story is that the delta nature of the mutual friction force gets transformed, or let's say modified, by the fundamental solution of the Gaussian of the diffusion equation, which is a Gaussian. And this is the approach that we have used, which I said is consistent with the physics actually going on at those scales. So the last innovation of our model is the fact that we separated the numerical processes. So the process dealing with the normal fluid velocity and the process dealing with the temporal evolution of the vortex tangle. So we put in two processes, meaning that they could run on two different nodes of a cluster. And then we implemented MPI protocol communication for a message passing interface in order to communicate the normal fluid, which was computed from the process that computed the normal fluid velocity, to the one that computes the temporal evolution of the superfluid vortex angle, and the mutual friction force, vice versa, from, in this case, process 1 to process 0. So from the process which deals with the temporal evolution of the superfluid vortex and the normal fluid flow. This allows a lot resolution in decent times of a lot more of degrees of freedom. So, for example, we went to a normal fluid grid, which is 512 cube, compared to the past 128 cube or even 40 cube. We also went one order of magnitude higher in the number of discretized points on the vortex length. This therefore allowed us to solve a wide range of scales, which, as you've seen, it is crucial if you want to investigate superfluid helium, because it's there that you can really see the similarities and differences between classical and quantum turbulence. So what results we have obtained with this method? So okay, we were quite let's say ambitious in the sense that we wanted to face to tackle, to investigate an experiment whose results actually have puzzled the community since when they were actually performed. So at the early 80s in the Max Planck, by the group of Schmidt. And these are the results were published in this series of papers. And so the system is quite easy, at least to describe, certainly not to perform. So you have large scales rings were created in the superfluid helium by pushing superfluid helium with a piston out of the cylinder. And this created this large scale vortex ring, which is here indicated in blue and red. And so actually in red, you see here I've indicated, this is a cross section, the superfluid vortices, which are embedded in a normal fluid torus. And actually, in fact, what happened here is that with this, with some acoustic revelators, so that you have some first and second sound emitters and receiver, they measured the position with respect to time, so the velocity, the circulation of the structure, and the vorticity distribution inside the torus. And what was found was that those structures were made up by more or less 2,000 superfluid vortex ring, and the two circulation, the normal fluid and superfluid circulation, were of comparable magnitude. And what was found actually is that this large-scale structure traveled for a long distance, so for a distance which is larger than 20 times the radii. And actually, this was only because of the limit of the experimental apparatus, because they reached the end of the apparatus. And these, importantly, all what they measured was independent of temperature, and they went from a temperature of 1.3 Kelvin, where there is 96% of the superfluid fraction, to 2.1 Kelvin, where the superfluid fraction is only 3%. So they had results which were, the dynamics was independent of the temperature, so independent of the friction. These experiments, the results of the experiment could not be explained with the one-way coupling model by Schwartz, so the kinematic model, the vortex filament method, because in this case, the dynamics was dependent on the temperature, and the distance traveled was a lot smaller. So here I just reported some characteristics of the experiment, and important is that you have to focus on more or less is that there was a large number of superfluid vortex rings. So what we have done is that we wanted to reproduce this experiment. We want to understand more of why these experiments, why these results when the kinematic model wasn't able to explain. So we started with, for the superfluid, we started with a toroidal vortex bundle, which we can see here on the right. And here on the left, you see the cross sections of these of this vortex tangle, of this toroidal bundle. And well, I have to say here that this is a regular hexagonal lattice, but actually we performed the same simulation with the random arrangement in the same toroidal geometry. So this geometry is defined by the outer radius r and the inner radius a. And so if you look at the values of r, a, and n, you see that it's one order of magnitude smaller than what was what characterized the experiments, but this is because of the computational constraints. But actually we can see that the radius, we chose these numbers because the radius r over a is the same as the one in the experiments. So for the normal fluid, which here you see in blue, we've chose a normal fluid vortex ring with the same circulation as the superfluid, and with the Gaussian distribution of vorticity. So what we obtain, and I have a movie which I want to play, which is hope you can see. So I will play it several times. So you see that after initial leapfrogging, collective leapfrogging, the toroidal vortex bundle, even if it loses some vortices, it remains compact. Of course, compared to the initial distribution, compared to the initial distribution, what you have is that the vortices is spread a lot broader inside the normal fluid vortex ring. And very importantly, what we find that it travels for a distance which is about 14 diameter. So a comparable way, is comparable to the experiment. And so here we see that there's a snapshot of this evolution. And this here you can see with the solid blue line, the evolution, the temporal evolution of the vortex length, which is a proxy of energy. And we see that in fact, it decays very, very slowly, okay? So what we did is that we did another simulation at t equals 0. So at t equals 0 meaning that there's no normal fluid, so it is full use of R. And we see that although, of course, the spatial spreading in the interior is a lot smaller. It is even quite absent. We see that there are also here reconnections, and in this case, the reconnection trigger carrying wave cascade, which goes on for many wave numbers because there is no dissipation with the normal fluid. So the dynamics is different from this point of view. But if we see the energetics here, so the length, which is a proxy of energy, here indicated with the green points, you see that is almost the same. This is very important because at t equals 0, there's no friction, and at the temperature which we performed the simulation, which was 1.95 Kelvin, you have the same dynamics from the energetic point of view. This means that the coupling, which is between the superfluid vortex, superfluid vortices and the normal fluid, this coupling, which is arises from the friction, actually kills the friction itself. And this is, you can see the coupling, and you can see here, this is in green and blue, you see the vorticity of normal fluid. You see that all these small circular patches are the vorticity which the superfluid injects in the superfluid vortices inject in the normal fluid. Then we did here is so in the third row, you see a simulation with the old vortex filament model by Schwartz, so a kinetic simulation where the normal fluid is imposed, as said, and in this case, imposed to 0. What you see here is that the bundle spreads very rapidly, and so at the end, there's no more any coherence, and so you're left with a collection of a set of isolated quantum vortex ring, and which shrink in an isolated way. And in fact, the temporal interval where they shrink is comparable to the lifetime of a single isolated vortex ring, and this is seen here. And in fact, this tau zero, tau naught is the lifetime of a single isolated vortex ring, and the length is this dashed line. So you see that it goes very quick. It is a lot dissipative, and it goes to zero very quickly. Very interestingly, I mean, at least for us, is the fact that if you use the coupled simulation, but starting with the initial quiescent normal fluid, which is that line, what you see is that after a first in very small temporal interval where the dynamics follows the old vortex filament, then there is a change. So the length actually does not decrease anymore, but then it even increases and then slowly decays. This means that this is the coupling which has excited the normal fluid in a way that to reduce the friction. So also in this case, as with respect to when we start with normal fluid vortex ring, here we have the coupling, and it's very important. I want to stress this effect. The coupling reduces the friction, so reduces the dissipation. So then we've started the same simulation with the smaller ring, with the smaller bundle, and it's here indicated in red, and we see more or less the same behavior. So here we report the dissipation. So the red and the blue, lines correspond to the red to the smaller bundle, the blue to the larger bundle, and you can see that the dashed line, which are the old kinematic model by Schwarz, so the vortex filament method without coupling, they are a lot more dissipative. And actually here, if you look at this dot dashed line compared to the dashed line, is where you have in both cases the initially quiescent normal fluid, but in one case it is imposed, so there is no coupling, the dashed line, and the dot dashed line there is the coupling, and you see that the dissipation goes a lot more rapidly to zero because of the coupling. So to sum up this dynamics and to try to convince you that superfluid helium can be considered, can be depicted as an active fluid, what is going on? So we have a collective vortex interaction between all the vortices, which brings to a rotational motion of the vortices inside the bundle. This steers the normal fluid via the mutual friction force, which is proportional to the velocity difference. But this implies that there is a reduction of the difference of the fluid velocities. So the two velocities tend to match. This means that the mutual friction tends to zero, and this enhances the Worsted lifetime. So the friction reduces the friction itself and hence the dissipation. This is very similar to what happens in active fluids, where you have that collective behavior. You have that energy saving mechanism emerges from collective behavior, and this happens through what is called hydrodynamic cooperation. But however, in this case, it is mostly a two-way coupling. So it means that what you have is that, for example, the bacteria interact with the aqueous suspension, or the fungal spores in air, also the cyclists with air. So it's so they might these only interact hydrodynamically, so not directly. They can only interact directly, for example, with a two-body collision, so very short range. Okay. However, our system actually is richer because it is a four-way coupling, because all vortices interact with all vortices, and is a long-range BSOR interaction. So in our case, we're not anymore in a two-way coupling, we are in a four-way coupling. And some similar studies could be, for example, realized in when you have electric charges or magnetic dipoles diluted in dispersed in a viscous fluid. So to do a summary of my presentation, so we have developed a fully coupled algorithm named Foucault, which tried to improve the physical modeling of the mutual friction force using a classical low-risk number fluid dynamic approach, and also with using a physically consistent distribution of this force among the vortex point using the physics that happens at these levels. This the results which you obtain with this algorithm reproduces the experimental results which have puzzled the community since the early 1980s. And we think that it is very important because it is a broader significance to our work, because actually some energy saving mechanisms are very similar to the active fluids. For example, if you think if you see the difference between the coupled simulation and the one-way kinematic modeling by Schwartz, there is a very rapid dispersion in the second case, or in the first case, it remains coherent. And this is actually the same thing that if you think it happens in cycling, when you have the peloton, where you have cyclists drafting when it's on flat, but when energy saving mechanism works, or when they go uphill, then you also, in that case, you have a spreading. Okay, so this perspective of our work is that we are implementing now the vortex dynamic on GPUs. So it's an n-body computation on GPUs, but however is a bit more complicated, because it's not like having to do with, for example, astrophysics, where you have to compute the force between planets, because in our case you've got curves which are oriented, and curves can change topology. And the goal with this new algorithm is to study intermittency, which needs a very wide range of scales, and also to have a better result statistics to compare with classical turbulence. So this first part will allow us hopefully to solve an even larger range of scales. And then the second part that we are working on is that we are including in the algorithm the dynamics of inertial particles. And this is very important because experiments in helium, visualization experiments in helium, are nowadays done mostly with solid hydrogen particles. So it's very important that these that to be able to model these experiments in order to interpret them. So, and we are liaising with the groups in experimental groups in Grenoble, Mathieu Gibert, and Marco Lamanti in Prague. And then also because we also want to see what is the reason behind this super diffusion of quantized vortices, which have been reported recently in literature, and we have to do with some correlation between the velocity of vortices. And with our algorithm, we should be able to solve also this, to interpret and understand the physics behind this. So with this, I thank you for again for the invitation and for attention. I'm happy to take any questions. Thank you very much.
So we have time for questions. Please.
Hi, Luca. Thank you for a nice talk. So I have a question.
Hi, Nico. I didn't see you.
So you showed that you need to generate like a very dense bundle of vortices to observe this enhancement of the lifetime of the vortex ring. Do you see the same if you have put a low number of vortices, or do you need like a large vorticity?
Thank you, really. Thank you very much, Nico, for your question. Actually, you only get energy-saving mechanisms if the vortices are close enough. This for two reasons: because the closer they are, the stronger is the steering of the normal fluid, and the closer they are, the smaller they are compared to the wake that they create in the normal fluid. So if you take, for example, the same number of vortices but more distant, you get less efficient dissipation reduction. So it is clear we've got simulation. I didn't put them up here, that the dissipation reduction is a lot smaller if vortices are further apart. And also, of course, if you put less vortices, you've got the same result. Here, it is really a balance between how how long this this vorticity structure which you inject in the normal fluid survives, so that the following vortices are able to gain. So it's like if cyclists are very close together or very far apart. If they're very far apart, there's no energy saving mechanism. If they're very close, the one behind saves a lot of energy.
Ned, come in, please.
Oh, hello. Thanks for the talk. And I would like to know if you face any numerical instability when you run those cases, and what kind of problem you face to evaluate numerically this problem. And if you could tell us which framework or language are you going to use for the GPUs. So if you can provide more information about the language and the framework. Thanks.
Yes, sure. So the numerical instability. So this is a very good question. So you have to be well, always, as you do numerical simulation, you have to be very careful on the landscapes that you use. So in the sense that, for example, when you in these cases, you have to be sure that the resolution on the vortex lines is sufficiently small compared to the average intervortex spacing, because the resolution on the lines, when two vortices are sufficiently close, then there is a testing for the reconnections. Okay, so if the resolution on the lines is larger than the average intervortex spacing, you of course you do reconnection, which wouldn't occur. In this case, it is a bit less restraint, because actually vortices, at least in the beginning, they are parallel, and so they will not reconnect even if very close. But anyway, this is the first thing you have to be careful on. The second is that in the t=0 simulation, you have to be aware that the numerical resolution cuts off the Kelvin wave cascade, and therefore this means that this means that there is that you are simulating more dissipation than the one that would actually be there. Okay, but this of course depends at which landscape you are interested in. Of course, also depending on the Reynolds number. In this case, we have a Reynolds number of about 1000, and so the numerical resolution for the normal fluid is still okay. But certainly, if you go to larger bundles or larger circulations or larger Reynolds number, then you have to use a smaller resolution for the normal fluid, as you know that it scales the relation between the large scales, so the size of the box, and the delta X scales like Reynolds to the 4/3. The GPU, because our code is written in Fortran, we might be a bit old-fashioned. We are using CUDA Fortran, which actually is now under, before it was elaborated by the Fortran group, by the Fortran group, so you need to have a Fortran group compiler, but actually now it's NVIDIA is directly giving the support for that. So actually in that case, it is okay to, I mean, it is straightforward to use CUDA Fortran. The problem with that, I mean, so that you will know, as I think that you know a bit of GPU coding, is the fact that you have to be very careful with handling the memory, because there are some memory bottlenecks from the large memory to the memory on the cards, and so you have to implement very carefully the n-body examples that you find in the literature, especially also because you need to change the topology, so the numbering of the vortex elements, which one follows the other one. It's a bit more complicated. Actually, it is really non-trivial task. So it will not be so immediate, unfortunately, I think.
Okay, next, please.
Hi, Luca.
Hi, Holly.
So in your video, you showed that vortices were being kind of kicked out and left behind. And then when it carried on, because it was a periodic box, I guess the tangle then starts interacting with those left behind vortices. Do they affect the numerics at all, or is it because there's only a couple, it doesn't really matter?
So of course, the results I showed for the length, for example, they only refer before they touch, okay? And because of course there is some interaction. From the point of view of the interaction of the vortex lines, it doesn't make really difference if you've got 160 vortices. If you've got the interaction with one, doesn't really change, destabilize the structure. What might change is the interaction with the wake of the normal fluid, actually, which you have left from the round behind. But actually, also in this case, I mean, of course, they are not exact, not exact simulation. In fact, we discarded all the result after a certain time. But also in that case, you have to compare the Reynolds number of normal fluid with actually the size and the intensity of these of the perturbation of the normal fluid. And actually, I mean, if I have to be honest, from a qualitative point of view, I think that it's useful also when you have when you interact with a few vortices of the wake. Of course, I mean, when you have to make some comparison with experiments, or I mean, put some results in publications, I mean, you will have to discard them because, of course, they're not realistic. But if you don't have much time to have a larger box, etc., at least you can understand what's going on.
Thank you.
Thank you. Please come in.
Hi, Luca. My name is Bruno. When you mentioned that the model is more capable of parallelization, and then you were explaining the model, the parallelization model using the MPI and the process, the separation, and the force in, I think it's the force field in one process and the velocity in the other. I saw V and F. I don't remember if it was exactly that. But is that the reason, the separation of force and velocity in different processors, that different processes that you can, that is what that makes the model more capable, or is other elements also?
No, so okay, so the fact is the separation, but it's the separation because at the present stage, but it is the separation because the separation allows you to do more or less Navier-Stokes computation on one machine and the superfluid tangle on the other machine. Before that, I mean, if you talk with people doing classical turbulence, they will laugh at you, okay? Because they have, I don't know how many nodes doing this, okay? Or even now they even went to GPU directly for the Navier-Stokes. However, the thing that you have to bear in mind when you deal actually with the superfluid helium turbulence, the numerical simulation, is that before it was all done on one node, and this meant that in the same node with the power of one node, which more or less it has increased, but it cannot go, I mean, beyond a certain level. You have to compute thousands of points, tens of thousands, even 100,000 of points, tens of thousands earlier, of okay, because somebody is in squared, and the Navier-Stokes equation. If you separate them, at least you gain like an important factor of time, because you are able to decouple them. You are also capable of doing some different time stepping. It is more easy to implement. So the main reason of that is that we had an important speed up, especially concerning the normal fluid. And then also and then a little, well, not sufficiently, we're not satisfied with that, but also for the vortex points. But the answer to your question anyway is yes, it is the separation which allowed us to run the processes on different nodes and so increase the speed.
Thank you.
Any other question? Okay, if there are no more questions, let's then again, Luca, please.
Thanks to you. And again, congratulations for the bravery and for the conference itself.
Thank you very much, Luca.
Bye-bye.
Bye-bye.